let's continue with our last discussion on scattering theory. जो आज हम करेंगे that would be the last time हमने बुनियादी तौर पर end किया था impact parameter. By impact parameter is a perpendicular distance from the target site. Yeah, so today we will develop initially some classical cross section in terms of that is the in terms of this impact parameter, and then we will move over to quantum mechanical description of scattering theory using Schrödinger equation, time independent Schrödinger equation. And then we would lead to, if we have time today, then we would lead to the concept of Green's function, do some initial calculation for the Born approximation, where your incoming particle, where the potential and the incoming particle energy have some relationship, as as uh, as compared to the other type of scattering sort of understanding, which is in fact the partial wave analysis. So let's start with the initial, with the classical cross section, how to how to determine the classical cross section, differential cross section, which is d sigma upon d omega in terms of the impact parameter. So what we need to, in order to develop this relationship, what we need to understand that in some actual experiment we cannot control the impact parameter on some molecular scale. Molecular scale, that is a scale which is which is in 10 to which is in a femtometer scale, or maybe femtometer less than femtometer scale. So what we learn from in fact from the passage of a single particle, we just only learn whether it is scattered or not scattered. So in some actual experiment, so let's start with the classical cross section. Classical cross section. So let's write some few points. So in an actual experiment, the when we say actual experiment, that is the one carried out in some accelerator, a particle accelerator, or some cloud chamber. We cannot control the impact parameter. That is, there are so many particles coming towards the target having different impact parameters and hitting the target system. So why we cannot control? Because we are working in a molecular scale. So in an actual experiment, we cannot control the impact parameter. And why is that? Because we are working in on a molecular scale. So what best we could do in such an actual experiment is additionally, we don't learn much about the passage of, don't learn much about the passage of the particle. Passage of the single particle. Yeah, of the single particle. So of a particle or of a single particle, what we learn is that it is scattered. We learn that it is scattered. So at most what we learn is that the particle is scattered. What we cannot learn, what we do not know about this experiment in some actual experiment is the passage of that particle. So some typical experimental setup would consist of a beam of particles where we have a well-defined velocity entering into the gas of target particles. These target particles or projectiles, they would then impinge on the target with a possible different number of impact parameter. That is what is unknown in some actual experiment. Uh, so we can write it. So uh, in a typical experimental setup, uh, that would consisting of consisting of a beam of of particles with what is known about these particles is the energy, kinetic energy. If the particles are free, that is, they are in unbound state, then what we know about them is their kinetic energy. And what do you mean by kinetic energy? That is, their velocities are well defined with well defined velocities. And these particles entering into a target uh, system or target particles. And then what happens? The projectile, they would impinge on the target particle with all possible impact parameters. And these projectiles are then sort of detected or counted by their passage through some device. And we have different types of detection devices. So there could be devices which are such as the reaction chamber, or just such as, for example, a cloud chamber, where you can in fact detect their passage. That is the passage of those projectile. Therefore, in such experiment, we effectively repeat the single collision experiment many times with a different or sort of random impact parameters. So it is not just a single experiment or single, in fact, event. There are many events, and we from those in those many events, the impact parameters are different. So, and they are different. Not We do not have any control over the impact parameter. So the impact parameter values are random. Yeah. So one could say that the incoming beam would be characterized by some flux of particles, and if we characterize that flux by n, small n, with a subscript I and c as incident, that is the number of particles per unit area perpendicular to the momentum of the beam. So we could think about beam of particles passing through a perpendicular area, and that perpendicular area is in fact perpendicular to the momentum of the beam. And so one could think about one could one could say the the incoming beam is this is basically characterized by beam is characterized by the flux of by the flux of by the uh, flux of particles, i.e. n I n c. N is the number of particles per unit area perpendicular to the momentum direction of the beam. That is the number of particles per area perpendicular perpendicular to the momentum. So we use the word momentum, indicating the direction of motion of those incoming particle, momentum of the beam, of the beam. And so, this is basically NINC. Then, so this is basically the input part, that is the number of incoming particles per unit area perpendicular to the momentum of the beam or the velocity of the beam. And then in the same experiment, we count the number of scattered particles. So we have small n inc is the number of incoming particles. We can denote the outgoing particles or the scattered particles by capital N with a subscript SC. So uh, then we could say in the experiment, in the same experiment, uh, we we basically count the number of particles, count the number of scattered particles denoted by, let's say, capital N SC. So this is basically the number of particles which are scattered. Therefore, one can have some sort of a rational picture, and in that rational picture, we can determine the cross section. So in this rational picture, we can say that the scattered particles, they hit some notional. Notional means that is we are thinking in our mind that there is some notional cross-sectional area, and this notional cross-sectional area is denoted by sigma of the target. Yeah. And so one could relate this scattered particles with the incoming particle using this constant parameter, which is known as cross-sectional area sigma. Yeah. This is the classical sort of approach जो हम यहाँ पर पहले देखना चाह रहे हैं, ताकि हमारी अंडरस्टैंडिंग डेवलप हो जाए कि एक्चुअली एक्सपेरिमेंट में हो क्या रहा है. So one could say therefore we can say that the scattered uh, particles hit some hit a notional जो जो हमने sort of imagine किया, notional cross section area denoted by sigma. And what is that? This is the area of the target. And then we could relate our two parameters, that is the number of scattered particle, n capital N scattered particle, they would be proportional to n inc, and we can in fact always remove this proportionality sign by thinking that there is some notional area or cross-sectional area sigma, which is basically some constant of proportionality. So n scattered would be equals to sigma times n, sigma times small n IC. And when one could picturize, sort of make a pictorial representation of this experiment by sort of drawing a picture. Try to draw a picture here. It is always very difficult to draw a picture on a device because sometimes it is not uh, controllable. So this is the beam of particles, incoming beam of particles. Yeah. And we have some cross-sectional area where the beam of particles are hitting. So this is NINC, the beam of particles hitting. And then we have this target. And let's say we denote this target by uh, sort of drawing some circles And so the beam of, so we would have some, uh, so we have some beam of particles, yeah, and they are reflected in some direction, yeah, and this direction we call it as d omega, which is in fact uh, dependent upon theta and phi, yeah. And so this we call as V of R, our target potential. We can have, so the beam of particle coming or hitting this targets, and they are scattered into some solid angle d omega. Yeah. So let's call this picture A. We can draw the head-on part describing the collision of the incoming particle as seen head on the target. So the head on the target would be something like कुछ इस तरह का पिक्चर हो जाएगा अगर आप इसको इमेजिन करें, इस पार्ट को इमेजिन करें. सो दिस कुड बी समथिंग एज इफ आई हैव दिस रीजन of the target characterized by some parameters. So it is the beam is hitting at different locations. Yeah, incoming beam is hitting at different locations, and so on. So what I am trying to, in fact, imagine is some area, this area, और इसको हम देख रहे हैं. So this is some area, and this could be something like this. So we have, so यहाँ से लेकर यहाँ तक का डिस्टेंस को हमने b का, ठीक है. दिस एंगल, दिस एंगल इज d phi, या. और ये जो strip है, that is a uh, differential impact parameter. This is basically dB, yeah. So जो in fact scattering हो रही है, that is going in from B to B plus dB, yeah. And so, and इसको let's say मैं इसका नाम दे दूं, इसका नाम दे दें B, yeah. And so one could think about uh, one could think about these incoming particle as NINC, which is in fact the particles, number of particles per unit area, per area, which is in fact perpendicular, and N into d omega is in fact किसके बराबर होना चाहिए? That would be something which is B times d phi into dB. Yeah, so this is something जो हम इसको कैलकुलेट कर लेंगे, जो अभी एक्सप्रेशन में कैलकुलेट हो जाएगा. सो बुनियादी तौर पर ये जो एक्सप्रेशन आपको नजर आ रही है ऊपर, एन scattered is equal to sigma times NIC, that defines this cross section sigma as some constant of proportionality area. That constant of proportionality basically represents some sort of an area that is the beam of particle incident on that area, and then there is some scattered beam of particle. So the expression for NC, which is in fact sigma times NINC, defines the cross section as a constant of proportionality, as a constant of proportionality. And this constant of proportionality is in fact the area of the target system between the incident beam and the scattered beam. So this is in fact this is the mathematical description of this cross section, and this cross section basically would characterize the properties of interaction between the projectile and. So you see what we come down to, or the essence of the scattering experiment is to think about the cross sectional area, that is sigma, as characterizing the properties of interaction, that is the interaction between projectile and the target. Yeah. So this is the essence of the experiment, that when you do experiment in some accelerator, you try to find out the scattering cross section, because that scattering cross section carries the interaction between the projectile and the target. So what is important here, the cross section characterizes characterizes the properties of interaction between between the incident beam of particles and the target particle. So that is what we are required to determine. And then if we would go into further detailed information about interaction, what we obtain is by counting the number of scattered particle, which are basically scattered in some solid angle d omega or delta omega. And this solid angle would be would have a dependency on theta and phi. So the detailed information that would be obtained, information about interaction, uh, how you obtain is obtained by counting the number of scattered particles NSC into a particular direction, into a particular direction characterized by theta and phi. Yeah, so this is some particular direction जिसके अंदर basically particles are scattered. Yeah, and so the impact parameter जो हम निकालेंगे वो in terms of d omega निकाल रहे हैं, d omega निकाल रहे हैं means in terms of the solid angle निकाल रहे हैं. So इसका मकसद हो गया, one could write this as equation क्या बन रही है. So we have n scattered, and that this n scattered times delta omega, which is in fact your solid angle or a differential solid angle, which is equals to sigma times delta omega into n IC. Yeah, n incident. So यहाँ पर sigma delta omega is some area of the target which scattered particles into some solid angle d delta omega. So what is where where uh, where we have sigma times delta ओमेगा ये क्या चीज है? इज द एरिया ऑफ द target which basically scatters particles into the solid angle omega, into the solid angle delta omega. So this is in fact what we are. So for a small solid angle, ये हमने delta omega का. Now we could think, since we are working in the domain of in a molecular scale, then we need to think about solid angle as being very small, or as being in a scale of a molecule or molecular dimensions. Then instead of using delta omega, we could think about those solid angle as d omega. Then the cross section would be sigma d delta omega. That would then become to some element of the solid angle d omega. So it means that for small solid angles, that is d omega, the cross section sigma delta omega becomes proportional to the element of the solid angle, to the element of solid angle d omega. So d omega is an element of solid angle, and so one could write this expression in terms of a small solid angle as n scattered uh, d omega, which is equals to d sigma over d omega in an element of a small solid angle, which is d omega times NIC. Yeah. So the differential scattering cross section. So इसको कैसे, अगर इसको हम पढ़ना चाहें तो कैसे पढ़ेंगे? This is differential scattering cross section in a small, बल्कि in a small नहीं, in an element of solid angle d omega. Yeah, so this is how we in fact study sort of read this statement on the right hand side. The ये जो quantity है d sigma upon d omega, इसको dcs से भी जाहिर किया जाए. dcs का मतलब differential cross section. Yeah, so one could also in a short hand notation, so we could also think about the quantity d sigma over d omega is also denoted as DCS. DCS का मतलब differential cross section. Yeah, so this is sometimes used in certain books. Now, इसको हम ये नहीं समझेंगे, that is it should not be understood as differential of cross section. That is ये d sigma upon d omega नहीं है, derivative of क्रॉस सेक्शन नहीं है. इनफैक्ट इट इज़ अ डिफरेंशियल स्कैटरिंग क्रॉस सेक्शन. सो फर्क है इन दोनों चीज़ों में. फर्क है से मुराद ये कि व्हेन यू से डी सिग्मा as a derivative of a sigma, then this would be some derivative of certain quantity. So it should not be understood as a differentiation of cross section, but mere it is in fact certain type of a notational description. Yeah. So one must not understood this as a differentiation of cross section sigma, but it is it is it is a mere um, notation. That is d sigma upon d rho. It is a sort of a notation. So now defining cross section in let us now define this cross section as some deflection function. What do you mean by deflection function? So deflection function would be a function which would be a function of the impact parameter and the angle phi and angle theta. So so one could think about the elementary surface area surface area uh, on some on the target, which is basically crossed by the incoming beam of particles. Elementary surface area crossed by the by the incoming beam of particles. वो क्या हो जाएगा? So we could think about sigma times d omega, and this is nothing but b times d phi into db. db is the differential impact parameter, and so one could think about these quantities, that is deflection function, by combining the expression जो हमने पहले निकाली थी, that is this expression, ये expression. So we combine this expression with what we now have calculated, and so combining the last two expressions, क्या हो जाएगा आपके पास? We have b d phi db एन आई एन सी दोनों साइडों पर मल्टीप्लाई कर ले, विच इज इक्वल्स टू किसके बराबर? डी सिग्मा अपॉन डी ओमेगा टाइम्स डी ओमेगा एन आई एन सी. So this is basically now the relationship between the differential scattering cross section and the impact parameter. So one could say then, और यहाँ से निकल कर आ जाएगा आपका relationship, that is the deflection function. So one could think about uh, d sigma upon d omega. अरेंज कर लें इसको. So that would be b db d phi upon d omega, और हम इसको लिख सकते हैं हम इसको लिख सकते हैं न्यूमरे राइट हैंड साइड पर जो इक्वेशन है हम उसको लिख सकते हैं बी डी बी डी फाई divided by this is d omega can be written as d cos theta. Cos theta is an argument of d into d phi, or this can be written as b db d phi upon sin theta d theta और आपके पास डी फाई या ये डी फाई और ये डी फाई कैंसिल आउट हो गए तो आपके पास जो जो रिलेशनशिप आ गई बी अपॉन साइन थीटा इंटू मॉड ऑफ डी बी ओवर डी थीटा या और इसको हम यू भी लिख सकते हैं रिलेशनशिप को यानी डी सिग्मा अपॉन डी ओमेगा दैट कुड बी रिटन एज बी अपॉन साइन थीटा 1 अपॉन mod of d theta over d b। इसको एब्सोल्यूट वैल्यू में क्यों लिखा है इसको हम the absolute value is basically here inserted why because the observed count of particles is always positive so अगर हमारे पास इस डिफरेंशियल का डी बी अपॉन डी थीटा या डी थीटा अपॉन डी बी अगर नेगेटिव आ रहा है that does not make any sense because the particles that is the scattered particle the count of the scattered particle would always be a positive quantity so that's why we have written here the तो इसको लिख लें the absolute the absolute value is inserted why inserted because or since the observed scattered particle the observed count of particles is always a positive quantity is always a positive quantity regardless of the sign of the sign of the term dB by d theta. Yeah, so that's why we basically write this expression as in terms of the absolute value.